Now we reach the topic of homology, which is what many people will say is really what algebraic topology is all about. Now, we could just write down the definition for homology. And really anyone can do that. You can just find that in the book. But what's a lot more difficult is trying to motivate where those definitions come from. When I first learned this material, I just saw the definitions presented to me in the book, and I learned them, and I was able to use them, and I can prove things with them, but I did not have any kind of motivation for why someone would introduce those definitions in the first place. So the purpose of this course is, I should say the purpose of this lecture, not this course, but the purpose of today's lecture is we do not want to just write down the definition for homology. We want to motivate it. We want to say where it is coming from so that we appreciate what is being done. Now, let's just say what we've been doing up to this point. So up to this point, we had X, this was a space, some topological space, and P was a point in the space, and we exclusively worked with this thing called a fundamental group. And the fundamental group, when you write it out, these are the classes of loops in X at P. So you have a base point, so this is like your space X. You have a base point, and you consider loops that begin and end at that point. And it's classes of loops because we have a notion of what it means for two loops to be equivalent. That's where we use homotopy. So these are really homotopy classes. These are homotopy classes of loops. And one thing about this group is pi 1 x comma p. It is in general not abelian. So sometimes it is abelian, but we saw that in general it may not be abelian, and it depends on the base point. Now, if your space is path connected, then we discussed that if you have a different point and you calculate this group, the fundamental group, then even though it is technically a different group, they are isomorphic to each other. So it's not the biggest deal in the world. So the 1 over here indicates one dimension. So one dimension in the sense that you have closed loops. Now, another way you can work with a loop is so I know we always talk about mapping the interval from 0, 1 into your space, but that's really in a way equivalent to mapping a circle into your space, because a circle is a closed loop. So you can regard this as classes of maps of this type. And then you can go one dimension higher and then talk about pi 2 x comma p. And then instead of being maps from the circle, it would be maps from a sphere into your space, where a certain point on the sphere is mapped to that base point. And then you have to come up with a notion of what it means for two such mappings to be equivalent. And then you have what is known as the second homotopy group. And then you have higher dimensions. So you can talk about pi n x comma p. And interestingly, that for n bigger than or equal to 2, they're actually abelian groups. They're all abelian groups. However, they are very hard to compute. So saying very hard to compute is an understatement. In fact, calculating the homotopy groups of the sphere around some point, it does not really matter, that's actually an unsolved problem in topology, as funny as that sounds. So if it's that hard to compute these groups, even for a sphere, that should give you an idea of just how difficult it is to work with. And usually most courses, in fact, I would say every course in algebraic topology, they never discuss this. That's like a more specialized type of topic that people learn if they decide to become a specialist in topology and they go further, then they might go on to learn something like that. So now what is homology? So we're going to introduce, so we will introduce homology groups. And they're going to look like this. It's Hn of x. And one thing you notice is there is no base point. And also, each homology group is an abelian group. So in contrast to the fundamental group, which does not need to be abelian, the homology groups will be abelian groups. And so how does one do this? So that's the point of today's lecture. We want to find a way to motivate the definitions so they feel natural, that it makes sense why we're defining things the way we're defining them. Just some history. Homology was also introduced by Poincaré. So that's pretty impressive. He introduced the fundamental group, and then he was not done. He said, I'm going to go on and introduce homology groups also. However, it was done differently. We're actually going to show the other approach, a more classical type of approach. The more classical type of approach is often it's often called combinatorial topology. And as we said in the first introductory lecture, combinatorial topology, it evolved into something that's a little bit better, and nowadays we call that algebraic topology. But I want to introduce the homology groups the modern way, the way they're done nowadays. And another feature of these homology groups is they're actually fairly reasonable to compute them for various spaces. There's actually a lot of different computational methods for computing these groups, and you have a lot more control over them than you do with the homotopy groups, or they're a lot easier to work with. Now, I think what would be helpful is let us motivate the definition of H1x, the first homology group of a space. And once you see how it works for dimension 1, it would actually be fairly straightforward to generalize it to higher dimensions. So that's like one of the nice things about this, is that the first dimensional case, you can argue, takes the most amount of effort to motivate, and then from that point on, all of the higher dimensions are motivated in the exact same way. So let's see how to do that. So what's going to happen here is that H1 of x, this is going to be classes. So it's very similar to the fundamental group. It's going to be classes of, and they're not going to, and instead of loops, it's going to be cycles. At the moment, we've not defined what a cycle is, but I would just say that the difference between a loop, so a loop versus cycle. So in the loop, there's a start and end, right? There's that base point. You begin at a point and you end at the point. In a cycle, there is no start and there is no end. I know that's not very formal, but that's maybe a helpful way to think about that. So in particular, this is actually what's going to make these groups abelian. They will end up being abelian groups. The reason why the fundamental group turns out being not abelian has to do with the fact that if you have two loops, when you multiply them by doing path juxtaposition. You move along the first loop and then you move along the second loop. So you have an ordering. You have a first one and a second one. So you have a start and an end. You have a first and a second. And because of that, that is what leads to the fundamental group not being an abelian group in general. But with the homology groups, you rather have cycles. So we're going to define what a cycle is. So you have cycles. And instead of being, so what do we mean by classes? So instead of being homotopy classes, these are going to be homology classes. And again, we have to define what that means. But the basic idea is you're going to have two cycles, whatever that means, and then we will have a notion of what it means for two cycles to be equivalent to each other. Just like we say that two loops are equivalent to each other if there's a path homotopy from one to the other, and then we say they're in the same homotopy class. With cycles, we would say that two cycles are in the same homology class if some condition is satisfied. So these are homology classes of cycles in your space, in X. And notice there is no base point anymore. There's no base point. So these cycles can really be anywhere you want. So like, for example, let's say we talk about the first homology group of the torus, let's say, and we want to calculate what that is. Well, what you can immediately notice is you can draw a cycle. Again, I'm not defining what a cycle is yet, but we will do that later. But for now, just think of it as a closed loop. So here you have a cycle, and maybe here you have another cycle. Right? You have a cycle there, and you have a cycle there. So in the fundamental group, you're not, if you're drawing this one, you're not allowed to draw that one because the base points are different. But when you're dealing with homology, you are allowed to draw these. It does not really matter where you begin and end, as long as you have like this cycle, this cycle that closes in on itself. So you would have something like this. And you can probably guess, because this is similar to what happened with homotopy, that these will probably be equivalent. They will be equivalent to each other. And the simple explanation is because you can slide that one into position. So they will be in the same homology class. But if you draw one going around, let's say like this, let's say, then that one would be in a different homology class, because that one you cannot slide into position to be aligned with the red ones. But now we want to make this a little bit more rigorous. So let's therefore begin with the following definitions. So actually, I'm going to do something that's a little bit unusual. I'm going to begin with the wrong definitions first. That's not the way people normally do it. And then we'll put it in the way everyone else does it. And hopefully by doing that, it will motivate the subject a little bit better. So we're going to, our definitions will be, quote, wrong. Obviously, there's no such thing as a wrong definition. You can make your definition be anything you want. But what I mean is the notation and the language that we're about to use is going to be incorrect. It's not going to be the way it's presented in the book, in the topology book. But then after we get the motivation, we'll fix up some of our notation so it's more in line with what you see in the book. But I think this would be the better way to do it. So let's define, so let us define the following object, C1 of x. So this is going to be, these are going to be one-dimensional chains in x. And what is this? This is by definition. This is by definition. This is the way we're defining it. This is the free abelian group. So previously, in the last class, we talked about free groups. So a free group is when you have a set of generators that have no relationships on them. But this is a free abelian group. So there's only one relationship, and the one relationship is everything commutes. So you are allowed to interchange two things together, and that is it. So this is going to be the free abelian group generated by all paths. And what is a path? It is a function from the unit interval into x. So if that's not clear, so to clarify, so if C is an element in C1 of x, then C will look like this. So it's a free abelian group generated by paths. So you're going to have a bunch of paths, let's say F1, F2, and then you might have a coefficient, A1 plus A2 plus, call it this, AN, FN, where each Fi is a path. So that's a path in X. And every coefficient is an integer. And what I want to say here is this is a formal sum. In other words, this does not mean anything. Like, you would think that this is a function and that is a function. So you're adding two functions together. So that's what you would think. You're adding two functions together. But the problem is, this is a topological space. And because it's a topological space, if you evaluate the function at a point and you get an element in your topological space, does not mean you can add two elements in X together. That would not make any sense. So we call this a formal sum. So this should be similar. This should remind you of polynomials. So like, for example, when you write something, let's say x1 squared x2 plus x1 x3, what is x1, what is x2? So in a polynomial, so in algebra, when you talk about polynomial, the polynomial ring, for instance, you talk about like the polynomial ring. These are indeterminates. They're just formal symbols. Now the idea is that you can take those symbols and you can substitute numbers in places for x. But in algebra, they're just indeterminate symbols and nothing more. That's all what we mean. It's just, if it makes it perhaps a little bit easier, you can think of C, so the chain, so C, that's your one-dimensional chain, as an unordered list of paths. So it's an unordered list because it's a free abelian group. It's an abelian group, so you can rewrite them in a different way. And the numbers in front, the coefficients, they just tell you how many times the path appears in the list. Okay, so how can you intuitively, so you can visualize C as a collection of paths in X. Okay, so if you write, let's say C is equal to F1 plus F2 plus F3, that would mean that in your space X, maybe this is F1, that's your path, this is F2, and then maybe this is F3. It crosses over like that, that's F3. And we do not put any kind of assumption about these paths. You might think maybe you want these paths to be joined together so you have like one nice continuous path. But no, we're not assuming anything like that. We'll put the extra assumptions afterwards, but for now, it's just, that's all what this is. It's just, that's the way you visualize C. That's all what it is. It's just a formal sum. Just think of it as a list, but you display the list as a sum because it's convenient to use that notation. Okay, so it's just a collection of paths. And if you put a number in front, let's say you put the number 2, then that's just supposed to tell you the multiplicity of the path. You're sort of saying the path appears twice. It's the same path, and it appears twice in the list. So for example, when we talk about the circle, sometimes you wind around twice the circle. And then you would say the multiplicity of going around the circle is 2. So the number is sort of just like the multiplicity of how often you go along a path. And if you change the sign, if let's say this is plus F2 and you make that minus F2, then you can think of it as just like changing the orientation or something. That's just like it's the same path, but it just moves in the opposite way. That's the way you can kind of think about it. So all it is just a list of paths and nothing more. Now I want to just give you a little bit of a warning just to make sure we understand each other. So here's a warning. So let's say X is the Euclidean plane, and F1 is the following path. F1 of t is the path t comma 0, and F2 is the path that's given by 2t. Okay, so when you visualize it, this is just a horizontal path going like this, and this is the same horizontal path but just twice as long. Now, if I was to ask you what is F1 plus F2, do not say, so you do not say that this is the path which is given by adding them together. Adding them together. Because what you're doing is you're taking a point in a topological space and another point in a topological space, and you're adding them together. In general, in a topological space, you cannot add. You're not allowed to. This is a formal sum. This is a formal sum. This is you're actually adding them like numbers. So it does not mean that. So the way you visualize it is, it's not very exciting, but the way you would visualize it is you would just visualize F1, and right below that, that would be F2. So that's the way you visualize it. It's just two different paths, and it's a list of two different paths. There's nothing else. So the only way you can combine, so also, let's say F3 is the path that's given by, let's say, negative t comma 0. So that would be the path going in the opposite direction. Then if you were to do F1 plus F3, that is not 0. And what is 0 here? 0 is the formal, it's the formal 0 in among one chains. Among one chains. So one chains, that is a group. That is a group. And the identity element we just denoted by 0. So you might think that because this path goes in the opposite orientation, you actually just leave it like that. You will visualize it, so this is the way you would visualize it. F1 will go like this. And F3 will go like that. And I know it's tempting to say that maybe they're supposed to cancel each other away because they're pointed in opposite ways, but we'll get to that later on. Like in the definition for now, there is no cancel. It just remains the way that it is. That is it. Just remain. That's all you do with it. You cannot do anything else. The only way you can combine, the only time you can combine chains is when it is the same like term. It's just like polynomials. Just like polynomials. So for example, if you have x1 plus x2, well, that's just x1 plus x2. There's nothing else you can do with it. But if you have x1 plus 2x2, x1 plus 2x1, then that would be 3x1. So it has to be the exact same term. If it's the exact same term, the same identical function, the same identical function, in other words, the functions are the generators, then you can combine them together. So if you had, let's say, a function plus 2 times another function, then you can say it's 3f because that's a formal sum. If it's the same identical path, then you can just add it in a formal way together by just, the coefficient is just telling you how many times it appears. And this should make sense because all you're saying is this is some kind of path, right? This is some kind of path, and then this is the same path appearing twice. So you have the same path on top of each other 3 times. And if you interpret this as representing a list, an unordered list of paths, then you're saying the path, the same exact path appears 3 times in the list. And then from that interpretation, it then makes sense. But you can only combine them together when it's the exact same function, just like in a polynomial. So this is a bit of abstraction, which you might find a bit rather bizarre, but this is how it works. And also, okay, also let me maybe do this. Let us also define, and again, this is going to be wrong. Later on, we'll fix it, but for now, this is the way we're going to do it. Let us also find C0 of x. These are going to be 0-dimensional chains in x. And all it is, this is the free abelian group generated by all points in x. Okay, so the difference between C0 and C1, C1, you visualize it as a list of paths, a finite list of paths. Maybe I should have said that, a finite list of paths. And you visualize C0 as a finite list of points, just points that have been selected in x. And the interpretation here is exactly, it's a free, so here's something very funny. So let's say x is the real numbers, okay? So let's say you pick the number 5, that's an element in C0 of x. And then you pick the number 3, that's another element in C0 of x. Then 3 plus 5 is not 8 in C0 of x. And that's basically, if this is like a polynomial, let's say this is a polynomial term, x1, x2, that's not x3. That these numbers are being treated as generators. They're not being treated as real numbers. They happen to be real numbers, but you're not thinking of them as real numbers. So 3 plus 5, it's just 3 plus 5. This is supposed to represent, right? This is the real line, and that's supposed to represent the number 3 and the number 5. Okay? And if you have 3 plus 3, you would write that as 2 times 3, where the 2 in front just means how many times it appears in the list. That would just mean the number 3, and on top of it, you have the same number. So it's a list where the number 3 appears twice. That is not the same thing as 6. Okay? So, by the way, this is how you know that you're doing advanced mathematics, when you reach this. When 3 plus 3 is no longer 6, okay, then congratulations, now you're doing advanced mathematics, and despite that looking ridiculous, it suddenly begins to make sense. Okay, so now let's introduce something called the boundary operator. So let us introduce what is known as the boundary operator. And this is going to be a mapping. It's denoted by the del. Nothing to do with differentiation. We just really love to use this symbol in mathematics. And it's going to be a mapping from C1 of x to C0 of x. And here's what it's going to do. So say that C, so we have to pick a chain, a one-dimensional chain. And again, think of it as a list of paths. So then this is going to be some finite sum where each fi, this is going to be a path, and every coefficient is an integer. Then we define del, or the boundary of C. We're going to define it in a linear way. We're going to distribute the boundary operator on each path individually. So you define it in a linear way. But then the question remains is, how do you define the boundary? So how do you, so where? So now you have to just define the boundary of an individual path, of a single path by itself. And the way you do it is, you take the endpoint minus the beginning point. Okay? And here's the whole point. This thing that we get, this is, you see, this is now an element of x. And this is an element of x. Those are the beginning and endpoints of a path. And you're subtracting them. But you're subtracting them in a formal way. So whatever you end up getting, that's an element of C0 of x. Okay, that's what that is. And now we're going to be able to define what we mean by a cycle. Okay, so now let's get to the definition of a cycle. Definition, we say a chain, a one-dimensional chain. So again, you think of a one-dimensional chain as a list of various paths together, is a, let's call it a one cycle, a one-dimensional cycle, if and only if the boundary of that chain is equal to 0. And what do we mean by 0? We do not mean 0 as a number. We rather mean 0 as the identity element in the 0 among the 0 chains. Okay, and to appreciate this definition, let's look at an example. Okay, so suppose, so say f is the following path. This is f. It goes from some point P to some point Q. And let's say we have another path, G, that goes from Q to P. And let's set C is equal to F plus G. So this is supposed to represent, I mean, this is the way you're supposed to interpret this. You visualize a C as a collection of two paths. So it's this path and then that path. But you see, the whole reason for using the additive notation is that in contrast to the fundamental group, where you have a first path and you have a second path, here you do not have a first one or a second one. You could go along F first and then along G, or along G and then along F. It does not matter because this is an unordered list. But if you look at this path, it appears as if it's some kind of loop, right? It appears it closes back in on itself. So it's some loop. And so let's just see what the boundary is. So the boundary of C would be equal to the boundary of F plus the boundary of G. So you calculate the boundary linearly by distributing the boundary operator on each term in the chain. And now this would be, so the boundary of F, that's where you end minus where you begin. So that would be Q minus P. And then plus the boundary of G would be where you finish, which is P minus Q. So this would be P minus Q. Now, P and Q cannot be individually added together because this is a formal sum. But because P appears twice, and it's a generator in this free abelian group, it's sort of like the same monomial being canceled out of a polynomial. It's sort of like x1 minus x2, x2 minus x1. So even though the x2 and the x1 cannot be combined, these two can be combined. So then you have cancellation, and what are you left with? You're left with 0. So that's what you end up getting in the end. You end up getting 0. So thus, C is a one-dimensional cycle. That's what we call it. It's a one-dimensional cycle. So it's similar to a loop, but there is no start/end. So that's the way this is done. So the way you want to visualize one-dimensional cycles is you want to visualize them in almost the exact same way as the loop. I would say the other difference is that maybe you can also add this. Also, a cycle, a one cycle, can be made out of many individual paths. But a loop is just a single closed path itself. So as you can see, this cycle over here, if you look at what makes up the cycle, you have two paths. The paths themselves are not closed, but taken together, they give you a cycle. They give you something that's closed. Whereas when you talk about loops, when we talk about the fundamental group, we have a single path that begins and ends at the same point. So that's like the other contrast, that with cycles, you have lots of paths that are being used all at once. Okay, so that is the definition of cycles. So now, so we're getting almost, so we are getting close. We're getting closer to defining h1 of x. So we would say that h1 of x, this is going to be one-dimensional cycles in x. But the missing part over here is we have to, these will have to be classes of one-dimensional cycles, in x. So, and the name of these classes, they're not going to be homotopy classes, though it's a similar notion. They're rather going to be called homology classes. Homology classes of one-dimensional cycles in x. So that is what we want to get to. So the question here is going to be as follows. When do we say that two cycles are equivalent to each other? Or here's a different way to put it. So returning back to the fundamental group. So if f and g are loops at P, and if f is equivalent to G, so you have two different loops, but you treat them as the same, so in the same homotopy class, so then the homotopy class of f is equal to the homotopy class of G. And from here, it will then follow, you can then put the G on the other side, f times G inverse, that would be the identity, right? So that would be what you call, I guess, the constant. This is the constant loop. So if two loops are equivalent, then their difference, so we have to write it like this. We cannot write f minus g because in general this is not a commutative group. So this is the way you would write it. Their difference is homotopic to a constant, or in other words, you would write, i.e., f juxtapose the reverse, right, the reverse of g, because how do you find the inverse? It's the reverse path, is homotopically trivial. So what we want to do is, is pick two chains, let's say C and C prime. So these are chains. Well, actually, yeah, so these are going to be chains, which are cycles, which are one cycles. And we want to define what it means. So we want the notion of if you were to subtract them. So you see, it's very similar to doing this. It's two paths are equivalent if their difference. So this is the reverse. So the difference. If they're so you're going to subtract them. You see, this is sort of like the f. That's like the g, but it's reverse. So that's minus. We want to define what it means for their difference. Define what it means for their difference, c minus c prime, to be homologically trivial. So that is the direction in which we're going with this. So instead of using homotopies, we're going to do this a little bit differently. Now, the motivation for what we're about to do is inspired by what happens in the fundamental group. So in the fundamental group, let's say this is your space. It's an annulus, right? This is your space. It's an annulus. And let's say you have a path that goes around the hole. This is your f. And then you have a path, g, that does not go around the hole. Then in the fundamental group, you would say that f and g, they're not homotopic to each other. And the reason for this is because you have that empty space that prevents you from moving f into g. But if you can somehow fill the space in, if you can fill that space in, then f is homotopic with g. So that's the idea. It's not about using a homotopy to deform one path into the other path. It rather has to do with a different idea, that there's that space inside that is filled in. So how do we do this? So the idea is to say that the difference. Oh, okay. So maybe we can do this. We want to say that a one cycle is homologically trivial if the space inside the cycle can be filled in. Right? That's the idea. So imagine you have some kind of cycle over here. Okay, so maybe do this. So let's say this is your space, okay? And there's like a hole in your space. And let's say you have a cycle that does this. Then you would say that this cycle is not homologically trivial because the stuff inside of it cannot be filled in. But if your cycle went something like this, if that was your cycle, then I know I'm drawing my cycle like a loop. It seems like there's a beginning and end point, but that's just the way I'm drawing it. If the space inside of it can be filled in. So that's the idea. So we have to, therefore, make rigorous by what we mean by filling in and the space inside of it. Now, if you look at this picture, the region that it bounds, right, the region that it's going around, that's a two-dimensional region. Okay, that's a two-dimensional region. So you're going to pick a two-dimensional. So you're going to pick. So you're going to pick some two-dimensional region. Right? Maybe you pick some two-dimensional filled in. So what can we use? We can maybe use a square. Maybe it's most convenient to perhaps use a disk, a filled-in disk. But usually when people work in homology, they use triangles. It just makes the notation in the end work out a little bit nicer. But you can really do it with any of these shapes. So the idea here is, suppose we have a function, we have a map, and we have a map from a triangle. So this is a fully filled in triangle into some space X. So let's say, right, it's into some space X. So I'm going to draw the space as this. So let's say this square represents our abstract space. So instead of getting a path, the image of this triangle is going to look like some kind of curvilinear triangle. So in general, it's going to look something like this. This is a curvilinear triangle in X. Okay, so it's some kind of curvilinear triangle sitting inside X. And you want to say, and this is the observation that you want to do. Notice the triangle has three sides. So let's say you go counterclockwise around the triangle, like this. You go counterclockwise. So if you go counterclockwise around the triangle, you get these three. So let's give them a name. Let's call it A, B, C. So you would say that if you sum them up, A, B, C, what you can see, this forms a cycle. This is a closed path, right? They form a closed path. So this is a cycle, is a one cycle that is homologically trivial because it has space inside of it that can be filled in. So that right there is the idea that you would say, so here's how we're going to define, so going back here again, here's how we're going to define homotopy classes. If we have two cycles, C and C prime, we would say that they are homologically equivalent if we take their difference and we can make their difference be homologically trivial. So what does it mean to be homologically trivial? We would say, and I'm not being precise here, but we will make this precise very soon. You would say that if their difference, so C minus C prime, can be obtained as the boundary around some triangle. So you can find some kind of triangle, and maybe to be a little bit more specific, the boundary around some triangle mapped into X. Right, so you're mapping some kind of triangle, some filled-in triangle into X, and its image is a curvilinear. Its image is going to be some kind of curvilinear triangle in X. And now, if you travel along the boundary of this triangle, its image will give you some cycle in X, and you will say that two cycles. You will say a cycle is homologically trivial if it arises in such a process, if it arises from as the boundary going around some kind of triangle. And that's the idea. So instead of using homotopies, the idea is that you can fill in the space in between the cycles, fully fill it in, and that means the two cycles then become equivalent in this homology group. But now we want to make this a little bit more precise. So this is the idea, and now we're going to discuss the notation which you typically see in books that shows you how to do this. To define homology rigorously, it would be helpful to begin with what are known as the n-dimensional simplices. So let's start with, I think the easiest one to actually start with is delta 2. This is supposed to represent a two-dimensional triangle. And at first, it might seem reasonable to draw the triangle in the two-dimensional plane, but for notational simplicity, people realize it's actually more convenient to draw the triangle in three-dimensional space instead. So here's the way you would do it. So the notation, the way it works is, instead of calling it x1, you start with x0. x1, x0, x1, x2. So these are going to be points in three-dimensional space, and the condition that they satisfy is all of the coordinates are non-negative, and all of the coordinates add up to 1. So the way you would see this is, this is the x0 axis, this is the x1 axis, this is the let's say this is the x1 axis, and that's the x2 axis. Then you just, these would be like the extreme cases. 0, 1, 0, 0, 0, 1, 1, 0, 0, and then everything in between them gets filled in. So it's not a tetrahedron because it's only the blue piece, right? This is a triangle. So that's going to be the object that's going to play the role of filling in the region in between the chains. So this is the two-dimensional simplex. So it's a triangle, but you draw it in three-dimensional space. It might seem bizarre at first, but this is the way you do it. And then if you write down the one-dimensional simplex, well, I know that previously we talked about the interval from 0 to 1. That's a one-dimensional object. But if you recall, when the lecture started, I told you that I'm going to do things in a slightly incorrect way, just to make it easier to follow. But the way people typically do it is you're going to replace that interval instead by a line segment in two-dimensional space. Now, of course, these two spaces are homeomorphic to each other, so it's not a big deal, but it's just the way the notation works out. So this would be x0, x1 in R2. And the condition would be that the coordinates are non-negative and that the coordinates add up to exactly 1. So this one would look like this. These would be the extreme cases, and it's a line. That's why we call it delta 1, because it's a one-dimensional object. It's just a line. And of course, this is of course homeomorphic to the interval from 0 to 1, but we rather use this notation. Maybe while we're here, we can also write down delta 0. So delta 0, this would be x0 in R, where x0 is equal to 1. Okay, so this is just the number 1. It's the set containing the number 1 and nothing else. Okay, so now that we have this, we can talk about mappings from these simplices, and of course, you can go into higher dimensions. Maybe we'll just write down one more for the sake of completeness. So delta 3, so this would be a tetrahedron, but it's a tetrahedron that's sitting inside four-dimensional space, so you're not going to be able to see it anymore. So the notation is you start with 0. You start counting from 0. So this is going to be in R4, and xi are non-negative, and the sum of each of these coordinates adds up to exactly 1. And you will see the benefit of this notation as we go on. And now, let's say this. So previously, we said that C1 of x, so this was the free abelian group generated by all continuous, I'm not sure if I said the word continuous, but of course it's understood that they're continuous, by all continuous maps from 0 to 1 into x. That was a more natural way to do it. But the way we're going to set up our notation is, instead of using the interval from 0 to 1, we're just going to replace it by the one-dimensional simplex. It's the same idea. The one-dimensional simplex is, of course, homeomorphic to that interval, so we might as well work with this instead. It's the same picture in the end. And then C2 of x. And this is something we did not mention before. Well, actually, before we do that, let's talk about C0 of x. So previously, so let's remove previously. So previously, we said that this was the free abelian group that's generated by all of the points in x. But we're just going to replace a point rather by the mapping, because a continuous map from the one-dimensional simplex into x will just give you a point in x, because it's just a single number being mapped somewhere in x. So we would just say this is the free abelian group generated by all mappings from delta 0 into x. And then you can define C2 of x. So this is going to be free abelian group generated by all mappings from delta 2 into x. And the way you visualize this is you want to think of these as paths So one-dimensional. C0, you're going to think of these as points. And these, you could think of them as perhaps surfaces, maybe surfaces, but maybe you can also think of them as triangles, perhaps, or surfaces, / surfaces that are sitting inside X. So it's just the image of this mapping that's going to give you some kind of curvilinear triangle that's sitting inside X. So, and in general, of course, so in general, we have Cn of X, and we call these the n-dimensional chains in X. Sometimes people say n chains in X. And to make sure that we are following this carefully, because this is a free abelian group, it's not just a single curvilinear triangle. It's going to be a list of curvilinear triangles. Maybe you have one here, maybe you have another one there. It's okay if they overlap or whatever. The various conditions that we're going to put on those triangles, on those mappings, come later. But for now, we do not put any kind of restrictions on them other than the fact that those are continuous mappings. So that's the way we define these chains in general. And now we need to talk about orientation. When we draw a path, there's a very natural orientation. This is the end, and that's the start, right, from the small number to the big number. But what if we replace the interval instead by the one-dimensional simplex? So if you replace it by the one-dimensional simplex, then here's the picture. So the one-dimensional simplex will go like this. And we'll go like that. So that's the one-dimensional simplex, and you're mapping this into X. So because of this, it is no longer clear which one is first and which one is second, right? It's now a pair of numbers. So which one should be first and which one should be second? So let's adopt the following convention. So let us orient this line as follows. So it'll be a line going upwards like this. So this is where you start, and that's where you end. So you have this oriented path in X. Or to put it differently, you're going to start by setting x0 is equal to 1, and you end by setting x1 is equal to 1. So there's two coordinates, right? There's two coordinates, x0 and x1. So when we work with these simplices, when we write down coordinates, we write them starting from the number 0. So then the last coordinate then matches the dimension of your simplex. So when you set the first coordinate, technically x0, when you set this equal to 1, you're down here, and when you set the other one equal to 1, you're over there. So this is the way you're traveling. So that gives you that direction by which you travel. And let's use this to define a mapping. So previously, we defined the boundary map. So the boundary map, it took a one-dimensional chain and it gave you a zero-dimensional chain. Or to put it more plainly, the boundary operator took a path or a list of paths, and to that list of paths, it associated points, right? And the way we did it is we took the starting point minus the ending point. Now, the part you have to be a little bit careful about, this might be confusing at first, is that C0 of X, this is generated by all maps that map the zero-dimensional simplex, which is just the number 1, into your space. Okay, so yes, we visualize it as a point, but the definition that we're using right now of the zero-dimensional simplex is that these are mappings that map the number 1 into X. So now, say that we choose something in C1. So let's say we call it G. Let's say we pick a chain in C1 of X. And so our chain is a formal sum of paths a n f n. Every coefficient is an integer, and every fi is a mapping from the one-dimensional chain into X. And we want to define, so we're going to set the boundary of C to be the boundary of, so we do it linearly exactly as before. We're going to apply it to each one. Like this. And now we have to define how the boundary operator is applied to every single such mapping, where the boundary operator applied to fi. So what we want to say, I mean, this is what we want to say. We want to take the endpoint, and we want to subtract the starting point. But let's see how this looks like in our new notation of simplices. So the way you get the endpoint, and technically, it has to be something. It has to be something in C0. So it has to be a mapping itself. So that's the part that's going to be a little bit confusing. But yeah, so how do you do this? So here's what you're going to do. You're going to take, now let's just recall how the orientation works. So the way the orientation works is you go like this. Right, you go like this. This is where you start, and this is where you end. So you first set the first coordinate, technically x0 is equal to 1, and then you set x1 is equal to 1. So this is the way you orient that simplex. And so to get the endpoint, you would say it's being evaluated at 0, 1 minus f at 1, 0. That's what you would like to say. But that technically is a little bit imprecise. And the reason why this is imprecise is because these two, these are not elements of C0 of X. It's a little bit confusing because previously, the way we defined C0 of X was the free abelian group generated by elements of X. But now C0 of X is defined a little bit differently. It is defined by all mappings that map the number 1 into X. So really, this has to be a mapping. And you see it's being evaluated at the number 1. So the correct way to do it is you really have to write it like this. You have to write it as fi, and you're going to write 0 dot minus fi dot 0. Now, what's the meaning of the dot? Well, the dot represents the variable. That's the variable. So fi 0 dot, it is a mapping from the number 1 into X. And fi dot 0, that's a mapping from the number 1 into X. I know that seems like kind of ridiculous to do that because you see this is a mapping, and when you evaluate it at 1, you end up getting exactly what you want. But I'm just doing it very carefully so that when we go to the next dimension, it's going to be the same theme. But that's really what it is. So now by doing it like this, this is no longer a point in X. This is now treated as a mapping from the from the 0-dimensional simplex into X. So the dot just represents, it gets evaluated on the 0-dimensional simplex. Now, yes, so this is what you're getting here. So a line, right? A line has 2 endpoints, right? A line has 2 endpoints. And yeah, so this is what you do, right? You just set. So you should notice what's happening here. when you set, so one of them is with a plus sign, so one of them is with a plus sign, and one of them is with a minus sign. I bring this up because this kind of pattern is going to emerge when we go up a dimension. The one with the plus sign, so you see what you're doing. You had a function. This was a function of two variables because this was a function on this one-dimensional simplex. So it has two coordinates. When you set the first coordinate equal to 0, technically this is the 0th coordinate. When you set the 0th coordinate, so this is sort of like x0, x1, x0, x1. So when you set the 0th coordinate equal to 0, you get a plus sign because that's an even number. When you set the x1 coordinate equal to 0, that becomes negative because that's an odd number. So it will have something to do with even and odd numbers, and then you just keep track of which one it's being set to. So now let's go up a dimension and define the boundary operator. So at the moment, we defined a boundary operator from one-dimensional chains to zero-dimensional chains. So if you give me a list of paths in X, from those list of paths, I can look at the endpoints of those paths and end up getting the points of X itself. That's the idea. But now we're going to go up a dimension. So now we will define another boundary operator, which we're going to call delta again. If you want to be careful, you can maybe index it like delta 2 or something. But usually, as is common in math, we get sloppy and we just call it delta again. But technically, it is a different map. So this is going to go from two-dimensional chains to one-dimensional chains. Okay, and how do we do this one? Well, so let C be a two-dimensional chain. So C is then a formal sum where each AI is an integer, and Fi, that's now a mapping from the two-dimensional simplex into X. And then we define the boundary of C in a linear way. So we simply distribute it on each piece individual. So that's exactly as we did before. And now the question is where, so we have to define the boundary operator on a single one of these. So this is what we have to figure out. How do we do that? So here's a picture. So the picture is that the two-dimensional simplex, so let's say this is x0, this is x1, this is x2. So the two-dimensional simplex, so that's the two-dimensional simplex. Be very, very careful here. This is not a tetrahedron, that's a triangle. So it's the blue part, it's not the stuff behind it. So it's just a triangle. And you have a mapping, which you're calling Fi, and that's being mapped into some space X. And the picture is that that triangle will produce for you some kind of curvilinear triangle in X. Now, what the idea here is so you see, when you have a segment, a line segment, you look at its endpoints. So when you have a two-dimensional simplex, if you go around the sides, you see, if you go around the sides of this triangle, you're kind of creating a cycle out of this. You're creating a cycle that is completely filled in inside, a one-dimensional cycle which is completely filled in inside. So now, how do you end up getting a cycle out of this? Well, the idea here is you're going to have three pieces that make this up. And you have to talk about orientations here. And when you're dealing with something like a surface, a convenient way to see this is imagine that this is your thumb. So this is your right hand. This is your right hand. And your thumb, imagine this, your thumb is pointed towards you. So now when you curl your fingers, well, with your thumb pointed towards you, as you go around the edges of the triangle, you're going to travel like that. You're going to get those three curves. And you want to find the image of those three curves. So now whenever you map a triangle into some space, there's two things that can happen. Either the triangle, either the side that is facing you gets mapped to the side that is facing you, or the side that is facing you flips over and now everything is facing down. So basically, does the thumb continue to face you, or does the thumb point in the opposite direction? So let's say for simplicity, say that the thumb continues to face you. So the side that you see, it's the side that you see in this picture. And so as you travel around these edges of the triangle, you're going to travel like this in this picture. So you want to get three pieces over here. You want to get these three pieces that make it up. So here's the way we're going to define it. So the boundary of this mapping, so here's how it's going to go. So let's say we want to get the lower edge. So how do we get the lower edge? The way we get the lower edge is by setting the x2 coordinate to be 0. So you would have fi, and you would set the x2 coordinate to be 0. And it's the x0 and the x1 coordinate that remain. So these are unchanged. So these are your variables, and this one has been set to be equal to 0. Now I want you to realize something very important about this. If this is x0 and this is x1, notice that x0 plus x1 plus 0, they have to add up to 1. So in other words, x0 plus x1 has to add up to 1. But what is that saying? That is basically saying is by setting the x2 coordinate to be 0, you're left with a function of one fewer variable, but the function that you're left with is now defined on the one-dimensional simplex. This is the one-dimensional simplex because the requirement is that these two have to add up to 1. Now, how would you get this edge right over there? Well, what you need to do is the x0 coordinate does not move, it stays as 0, and it's the x1 and the x2 coordinate that move. So this would be fi. So which one is that? So that's the x0 coordinate is set equal to 0, and it's the other two coordinates that it's now a function of. So this is now x1, x2, and the requirement is that x1 plus x2 have to add up to 1. So this new function that you're getting, it's a function of one fewer variable, but it's now defined on the one-dimensional simplex. Which you see, this is exactly what we want. We want to start with something that's defined on the two-dimensional simplex and create something that's defined on the one-dimensional simplex. And then, and then finally, in the end, we have the other one. This is the remaining one going like this. So this is going to be fi, and this is the one where you set the middle one equal to 0, and the other ones are your variables. So this is the x0, x2, and they have to add up to 1 exactly as before. And so you have a function that's defined on the one-dimensional simplex. And now let's determine the correct orientations. So notice that this first one, it's going, you see, it's going, x0 starts at 1, and then x1 becomes 1. So it's going in the right direction. So this one comes with a plus sign. The next one is the one going like this. So x1, so x1 starts at 1, and then x2, and then it finishes with x2 being equal to 1. So it goes the right way, so that's going to be plus again. And this one, where the middle one is set equal to 0, is this time you're finishing by setting x0 to be 1, but you're beginning by setting x2 to be 1. So you're kind of going the wrong, the correct orientation will go like the one-dimensional simplex. So in the one-dimensional simplex, this is the one that goes first. It's really going to go this way. So if you want to make it go the other way, so it's consistent with this picture, you're going to put the minus sign over here. Now, you could, of course, figure it out from a picture, but the easier way to understand how this works is you just look at even and odd numbers. You set So what you do is you set, so if you set the second one to be 0 and you treat the other two as the variables, then you get positive because it's an even number. This one is negative because you're really setting x1 to be 0. So it's all a question of which one you're setting equal to 0. So if it's an even position, it's positive, and if it's an odd position, it's negative. So now you have defined, and these are now functions on the one-dimensional simplex. So thus, the boundary of fi, that's now an element of the one, it's a one-dimensional chain. It's a one-dimensional chain. Okay, it's going to be a one-dimensional chain because these are functions of one fewer variable. Okay, so the dimension goes down by 1. And you can do this more generally. So in general, we have a boundary map from the n-dimensional simplex to the n-1. I'm sorry, not the n chains to n-1 chains. So for simplicity, let's say we take f to be a mapping from the n-dimensional simplex into x. So because this boundary map is going to be defined linearly on all such mappings, let's just assume we have a single such mapping. And then we define the boundary operator applied to this n chain in the following way. So we're going to take f, we're going to set the first coordinate, the 0th coordinate, to be 0, and then the other ones will remain, and that would be plus. Then we would have minus f. Then we would set the x1 coordinate to be 0, and then the other ones will remain, and it will alternate. So this will be plus, minus, then it will be minus, and so on. So that's the way that you do it. Now, the notation that people use is they often write it like this. So this is an alternating sum. So you can say I goes from 0 to n, because so it's an n-dimensional chain, but there's n plus 1 coordinates, so you go from 0 to n. So it's an alternating sum. And the notation that you can use is people write delta subscript I of f. And all this means is, this is called the ith face. So it's called a face because when you have a triangle, it has like 3 faces or 3 edges. That's called the ith face. And all what this is this is the operation of setting the ith coordinate equal to 0 and then keeping the remaining coordinates as the variables of the function. And you want to just observe that the ith face, when you do that, that's going to be a mapping from the n-1 dimensional simplex into x. That's kind of the whole point of this, into the n-1 dimensional simplex into x. So you're getting something that is therefore this is a formal sum of n-1 simplices. So by definition, we call this an n-1 chain. And this is the reason why the boundary operator takes you from this one to that one. So that's how the boundary operator is being defined. So now we can rigorously define, in general, what it means to be a cycle. So let's write down this definition. An n cycle in X is an element, is something. So it's an n-dimensional chain, so that the boundary of that chain is 0. And this, of course, is the formal identity element 0 in the n-1 chains. So that's what we call an n cycle. Now, to give you some, maybe some intuition, a 1 cycle can be visualized, and this is what we did before, visualized as a closed path in X. It's not exactly a closed path. It's made out of many paths. And by the way, I mean something like this. So you can have, let's say, this is one path, this is another path, then this is a third path, this is a fourth path, and then you have another path going. So let's say it goes like this, and then you have a path. So this entire thing would be called a cycle. So it's like two separate closed paths in X. Again, they're not really paths because it's a formal sum of paths, but that's the way you want to think about it, at least. And a two-cycle can be visualized as two-dimensional. You see, these are made out of one-dimensional simplices. Well, a two-dimensional simplex is a triangle. So it's basically an object that gets triangulated, right? Something that gets triangulated using two-dimensional triangles that fit together. And that's often what you think of as a surface. It can be visualized as a surface in X. And surface, you can say a closed surface. You can also say a surface without boundary. Now, this is slightly confusing terminology because closed here does not mean that it's a closed subset of X. That's not what it means here. And when we say without boundary, it does not mean that the boundary of that object as a subspace of X is the empty set or something like that. It's a little bit confusing because this is sort of like a homological closed as opposed to a topological closed. So rather what we mean is, so an example of a closed surface would be a sphere. This is a closed surface. You can also say it's a surface with no boundary. The boundary is 0. But if you have, let's say, a cylinder, this is not a closed surface. And the way you can see it is because a two-cycle, first of all, is a two-chain. And a two-chain is a formal sum of simplices, right? Mappings of simplices. So think of it as a list. So you have a collection. So imagine you have a collection of simplices here, curvilinear triangles that fit together in some kind of nice way. So let's say this is one piece, and then we have, this is one triangle, this is another triangle. So a bunch of triangles like this. So you have like lots of little triangles. So you kind of triangulate it into lots of different pieces. And now if you find the boundary, right, you find the boundary by going around, let's say like this. Notice that if two triangles are adjacent to each other, then these two paths, they're negatives of each other. So they formally cancel each other away when you calculate the boundary around that simplex. So if they're right next to each other, they cancel away, right? They're right next to each other, so they cancel away. But because, so what you're going to be left with is you're going to be left with this, and you're going to be left with that. So when you calculate the boundary operator, you'll be left with these two circles that are going around it. It's not going to be 0. But when it's a closed surface, it would mean that if you take your surface, if you were to triangulate it into lots of different little pieces, triangles like this together, it's just a list of these two simplices. Because all of them are adjacent to each other, that they keep on canceling each other away. And so when you calculate the boundary operator, you're not left with anything, and hence that's why you say it's a closed surface. So those are the ones we can visualize. One cycles, two cycles, three cycles would sort of be like a three-dimensional manifold, and that's something you cannot necessarily visualize anymore. But that's how it works. So that's the visualizations. But this is the definition. So this is the way we define an n cycle. So an n cycle is a chain whose boundary becomes 0. And you want to have visualizations for dimensions 1 and 2. And now I want to write down a proposition, which I'm going to put on the homework, and you try to figure it out. And this one says that d squared is 0. So what does that mean? It means that the boundary of the boundary is 0. So more specifically, what it means is that if C is some kind of n-dimensional chain, then if you take the boundary of that chain and you take the boundary of that, then you get something that's 0. Of course, assuming that assuming that n, I guess, is at least 2. Otherwise, you do not talk about negative dimensional chains, but let's not even go there. Let's not worry about that. And this should make sense, because going back to the simplex, so if you have the simplex, the two-dimensional simplex, how do you get the boundary? You just go around it, and then the boundary of C is then the cycle that consists of those 3. So it's specifically done in such a way that you end up getting a cycle. So when you calculate the boundary of a chain, you end up getting a cycle. Or to put it another way, so alternatively, the boundary of any n chain is an n-1 cycle. So when the boundary reduces the dimension and you get something that has no boundary anymore. So that's what we're saying. Now, so now we can finally define what the homology group is. So here's the definition. So Hn of x, this is going to be the equal to the set of all n cycles in X. And we have to identify them. And these are going to be what we call homology classes of all n cycles in X. So to put it more precisely, i.e., if C and C prime are n-dimensional chains, which are cycles, so that means, i.e., the boundary of C is 0 and the boundary of C prime is 0, then we say that C is homological to C prime. So we abuse this notation all the time in this class, but here it means homology. So C and C prime are homologically equivalent to each other if and only if their difference, when you subtract them, so you can subtract them because this is a formal addition, formal subtraction. This is a free abelian group. So it's formal, it's just a formal subtraction of them two in this group. So if and only if their difference is homologically trivial, So what does that mean? That means, so this is the picture that we were saying before. It's when their difference can be, you can find something of one higher dimension. So in other words, the space in between them can be filled up, and they become the boundary of that space. So if and only if their difference is the boundary of, let's say, sigma for some sigma one higher dimension up for some n+1 chain. You can find an n+1 chain whose boundary will give you the difference. So this is basically the picture we were saying before. I'm going to draw the picture using disks because it just makes the pictures a little bit easier to see. But what we're saying is, suppose you have, this is F going like this, and let's say G goes like this. And let's say the space in between them is filled up. Okay, then the idea is you can find a two-dimensional object, in this case, the disk, so that if you, let's say, travel like this around the disk, so you could map the disk into your space, so that as you travel like that around the disk, you will recover these two pieces. So in other words, the space in between them can be filled with something that's one dimension larger than them. Okay, so this is the way the homology groups are defined. So the nth homology group, it's the collection of all n-dimensional cycles, and you put an equivalence class. You say that two cycles are treated to be the same if you can find something of one higher dimension whose boundary will give you their difference. Now, I'm going to show you some examples, some visual examples to help out with the intuition. But before I do that, I want to show you the fancy way of defining homology. So this is the fancy way of defining homology. So we start, so if we have, let's say, four-dimensional chains, they get mapped to three-dimensional chains by using this boundary map. And the boundary map maps three-dimensional chains to two-dimensional chains. These maps them to one-dimensional chains, and these maps them to zero-dimensional chains. And then, of course, this goes on forever. So this is called the chain complex. So we call that infinite sequence. It's not a sequence of numbers, it's just a sequence of groups. We call that a chain complex. And then observe that if you compose delta twice, you get 0. So that would mean that, let's say, so if you go twice, so if you go directly from C4 to C2 by doing it twice, you get 0. Right? This is 0. That's going to be a 0 map, and so on. Because d squared is 0. That's what we mean. If you do it twice, you get 0. And you would then say the nth homology group. This is exactly identical to what we said before. So if the previous definition makes sense and you're comfortable with that, you can, of course, use it. But I'm just showing you if, let's say, you're looking this at Breton, he will, of course, do it the fancy, sophisticated way. So the way you get the nth homology group, so let's suppose you want to get the third homology group. So the way you get the third homology group is you're going to look at all of the chains that have 0 boundary. So that would mean all of the chains whose boundary map becomes 0. So you're going to look at what is known as the kernel of the map. So you're going to look at the kernel of the map that goes from C3 of x to C2 of x. So this delta map, this boundary map from this dimension to that dimension, you're going to take the kernel of that map, and then you're going to quotient, you're going to treat two things are the same if they're homologically equivalent, if you can find something in one higher dimension that goes into it. So you want to find something in here that goes into it. So the way you would say it, it's the image of this delta in that one. So you would quotient out by the image of C4 of x into C3 of x. So that is the, well, I mean, I'm using n over here, so I should really write this as, so this would be n minus 1, and this would be n plus 1, and that would be n. So that's the fancy way of writing it out. But the previous one, I think, is sort of a little bit easier to understand, even though we're technically are saying the exact same thing. Okay, so this is the definition of these homology groups. So today, we're just defining what they are. We get to the computations afterwards. We just want to define what they are, so at least we know how they're being defined. So now I want to get to some visual examples. And now let's conclude with some intuitive examples. As the semester progresses, we will develop tools that will calculate for us homology, and we will be able to justify these calculations, but just proceeding based on our intuition of what we think should happen. So let's start with this. Let us calculate the first homology group of the two-dimensional sphere and the second homology group of the two-dimensional sphere. And also let's do it for the third homology group of the two-dimensional sphere. And for the homework, we're going to put this somewhat interesting question on the homework, the zero homology, and not just of a sphere, but any space X. So that's going to be somewhat interesting to look at. It has an interesting interpretation for what that means. But let's just focus on the one-dimensional homology. So the one-dimensional homology of the sphere, this should be, so it's classes of one cycles. These are just basically one cycles. One cycles in the sphere. So let's draw some one cycles. Now, if you draw any one cycle, so here's like a one cycle, that's like a one cycle. Notice this one cycle, it is a boundary of this two-dimensional region. The stuff inside that one cycle can be filled in by a two-dimensional region. So you can find a two-dimensional region whose boundary will give you that one cycle. And that's what it means to be homologically trivial. All one cycles, right? All one cycles are homologically trivial. So the first homology group of the sphere, it's just going to be the trivial group. That's kind of interesting. The fundamental group of the sphere is also trivial. Maybe there's a connection between the first homology group and the fundamental group, the first homotopy group. And there is. We're going to see that connection later on. Now let's talk about the two-dimensional. These are going to be two cycles in S2, in the sphere. And how do we think of a two-cycle? We think of a two-cycle as a closed surface. So instead of a closed path, you think of a closed surface. Can you find any closed surfaces inside the sphere? And you should probably realize that the sphere itself is a closed surface inside the sphere. So the sphere is sitting inside itself. So the sphere itself is the closed surface. And the sphere itself is not the boundary of something that's three-dimensional. It's not a ball. If you had a solid ball and you can fill it in, then you can find a three-dimensional object, so namely the solid ball, and the boundary of the solid ball would be a sphere. But the space inside that closed surface is not part of your space. And because of that, the sphere is it's a closed surface, and it's not the boundary of anything. It's not the boundary of anything one dimension bigger than it. So because of this, it kind of makes sense that H2 should be isomorphic to the integers. Why the integers? Well, because if C is the two chain, which represents the closed surface, then C plus C is also a two chain. So in other words, you can keep on taking the formal sum. So you have the sphere is a closed surface, and then you can just take the sphere plus itself. So just two copies of the sphere, because two chains are just formal sums. They're just formal sums. So, and you can take it as many times as you want. So you end up getting a group that's isomorphic to the integers. Now what about this? This you should guess is 0. So you should guess that this is equal to 0. The reason for this is because three-dimensional, you want some kind of three-dimensional object sitting inside a two-dimensional sphere. That seems impossible. And because of that, you say it's 0. And again, we will justify this carefully, but that's just our intuition. Maybe your intuition should make you think that. Let's look at an example of a torus. Let's say we have a torus, that's X. So let's say T is the torus. We want to find the first homology group and the second homology group. And like I said, the 0 homology group, this is going to be homework. So on the homework, you'll actually figure out the 0 homology group for any space. And the third homology group, you can probably guess that's going to be 0, because the torus, that's like a two-dimensional object. And so it's not supposed to have any three-dimensional simplices sitting inside of it. So a three-dimensional simplex, that would be a tetrahedron. But what about these two? So let me do H2 first. So H2, you should guess that this is isomorphic to the integers. Now, why is that? Because you have to see, can you find any closed surface that is sitting inside the torus. You cannot pick a sphere because a sphere is not part of a torus. This part that goes like that, that's not part of the torus. So you can maybe draw this, but you cannot like close it off to get the other part of the sphere. So the sphere is not part of the torus. So the only surface, the only closed surface sitting inside the torus is the torus itself. Okay? So you would therefore guess, for the same reason as before, it's Z. And notice it's basically Z to the 1. The 1 is indicating basically the number of holes. So you have one hole of dimension 2, a two-dimensional hole. Now let's look at the first homology group of the torus. So cycles. So you can find a cycle going like this. That would be one cycle. And another cycle that you can find is the cycle going like that. And it feels like these two cycles, one that goes around the inner ring and the outer ring, should be different because, well, we're used to the fact that they're not homotopic to each other. So, and that would be correct. That would be correct. So so it will turn out that the first homology group will actually be isomorphic to 2 copies of Z, because you can use as many repetitions of the circle as you want and as many repetitions of the other circle. So you get 2. So you're getting that this is Z to the 2, and this power indicates basically how many holes you have. You have 2 holes, one going like this. So you have 2 holes of dimension 1. That's basically what you're saying, 2 holes of dimension 1. Now, here's something interesting. So let's say we go back to the torus again, like this, and we draw a cycle like this, and we draw a cycle like that. Why are these cycles, these are 1 cycles, homologically equivalent? So here's why. I want to draw a picture for you. You have to try to find something that is 2-dimensional and will give you and its boundary will give you those 2 cycles. So here's the way you do it. Just imagine this collar right here. So take this sheet of paper and wrap it around that ring. Now you should notice that these 2 sides, they get glued together. And the 2 outer sides, they end up right over there. And the orientation, so if you kind of go along the orientation, so if you go around to get a cycle like this, notice that these 2, when you glue them together, they go in opposite ways. So that means the 2 blue paths, these 2 blue paths that you get on the torus, they cancel each other away, and then you're just left with these 2. And these 2, you just have one going like this in one direction and one going in the opposite direction. And that's exactly the condition for being homologically equivalent, if the difference between them can be expressed as the boundary of a 2-dimensional object. And that's exactly what we're doing. We're finding a 2-dimensional object. I know we're not using a triangle here. It's just more convenient to draw a picture using a square. But you can find a square, and if you go along the boundary of the square, you find that the boundary of the you recover the difference. You get the difference of these 2 cycles. So the difference of these 2 cycles is the boundary of a 2-dimensional object. So you can find a 2-dimensional object which bounds the difference of those 2 cycles. So therefore, they are homologically equivalent to each other. So that's kind of like the reasoning over here. Maybe just to show you this example, let's say you have. So let's say you have a torus and a torus joined at a single point. So let's say T, 1 point union T. Then what is the first homology group and what is the second homology group? So the second homology group, can you find a closed surface? Yes, you can find the torus on the left and you can find the torus on the right. So this would be Z2. So you have 2 holes of dimension 2. Now for this one, you can find a cycle going like this, a cycle going around like this, a cycle going around this one, and then the cycle going around that one. So you would guess that this one is probably Z to the 4. And then, of course, you could be skeptical. You can say, well, what if you go around like this, right? Is this something new, or is it expressible in terms of the other cycles? So I understand that the intuition might fall apart sometimes, but We, of course, will develop computational methods that will do that for us, and that would be sort of our justification. But that's kind of like the way you think about it. And in a way, as we've said, it's measuring how many holes you have. So the number of copies of Z is sort of like the number of holes that you have in your space. And the homology is accounting on the number of holes.